In the previous lecture, I worked through the example. I believe it was 8.3 in Griffith's book, where we're looking at the momentum in the fields in a coaxial cable. And the result that we got was this equation, that the momentum in the fields is related to the potential of the battery, the current going through the coaxial cable, and the length of the cable divided by the speed of light squared. So what was the picture that I drew? Let's go back and take a look at that. Okay, so here is the picture where we have our battery right here. It's hooked up to a resistor, and now it's hooked up to that entire coaxial cable, which is essentially a conductor, a cylinder, a small cylinder in the middle, which is a conductor, and a larger cylinder on the outside, where current can flow. And it's just that the current that flows down the center comes around and flows back on the outer cylinder. Okay, so so what we ended up with this result, that this is our momentum in the fields. Now, we could consider this a different way and say, what if we were to have an adjustable resistor? So this resistor can now change. If I change a resistor, it's going to change the current. So an adjustable R is going to lead to a changing current. So therefore, we're going to have a di dt. Now, current is related to the magnetic field. So if I have a current flowing on the conductor, that's going to create a magnetic field. A changing current is going to lead to a changing magnetic field. Changing magnetic field means I have a changing magnetic flux, and changing magnetic flux means I'm now going to create a EMF, or a potential. I'll have a induced potential in this particular case. So this was worked out in chapter 7, and so if you go back to chapter 7 in the book, what we had was the electric field being created in this particular situation is mu 0 over 2 pi, the changing current with respect to time, natural log of the radius, plus a constant k. All of that is in the z direction. So this was equation 7.20 in the previous chapter. So, okay, so now I have this equation for the electric field. Like I said, K is just a constant of integration, or basically what you would get from the initial conditions of the situation. We know whether you started at a current of 0 and ramped it up, or, so what you would get is that. Now, what's the point? Well, the point is that if I now have an electric field, then I can calculate the force on a charge. So a charge that is moving down this conductor, the force pushing that charge is going to be the charge times the electric field. The charge is the linear charge density times the length times that electric field. Okay, so now we'll put that together. So my equation for the force is lambda L mu 0 change in I. There's divided by 2 pi in there. The natural log of A, so A is my, A is the radius of the inner conductor, plus my constant of integration. That's in the z direction. Okay, so that's one force, but there also is the force pushing the charge on the outer conductor. So that would be minus, because it's in the opposite direction, lambda L mu 0 over 2 pi di dt, the natural log of B, now the radius of the larger conductor, plus the same constant of integration times z, z hat. Okay, so that's the total force acting in this case. And so, okay, we can actually collapse this a little bit, and we would get minus lambda L mu 0 over 2 pi, the change in the current with respect to time, the natural log of B over A, and then the constants of integration cancel each other out in both cases. And all of that is in the z direction. Okay. Okay, so that's the force. But what we want is the momentum. So the mechanical momentum is equal to the integral of the force over time. And so if we look at what's above, all of those are essentially constants. The charge density is constant, the length of the cylinders is constant, mu 0 is a natural constant, the radii are not changing, we're keeping the radii fixed. Everything there is not time dependent, they're all static quantities, except for di dt. So in the end what we get for our mechanical momentum is minus lambda L mu 0 over 2 pi, the natural log of B over A in the z direction, the integral di dt dt. So when I integrate that, eventually what I get is the current. So I have minus lambda L mu 0 I over 2 pi natural log B over A, like so, in the z direction. So, okay, and so if we remember, once we got to this point, that VI was equal to lambda L over 2 pi natural log times I. There we go. So that the power is equal to that. So if I plug this in, I get P mechanical is minus VI oops, sorry. There's no L in here. So I get VIL over C squared. Or, basically VIL times mu naught epsilon naught. Keep dropping things. Okay. In the z direction. So essentially I get back the same thing we had before. So whether or not you work it out through just what is the total momentum in the field versus what is the force, or what is the force pushing on the charges, then you would get the same result we have here. So basically what we're trying to say is that the momentum in the field is going to be the momentum equal to the momentum that you're going to impart on those charges moving along the conductors. Now the last thing you have to be careful of is, one would say, wait a minute, what about that minus sign? How can we justify this equality if there's a minus sign on one derivation and a positive sign in the other derivation. And so where that minus sign comes about, well, the way that we can deal with it is the fact that I was pretty loose with this derivative, this integral, sorry, right here. I didn't, it's an indefinite integral. I didn't actually specify what the, which way that I'm changing the current. And so really the way to take care of the minus sign is the fact that I can choose how I'm going to be changing my current. So if I start with a current that's high and I adjust the resistor until the current goes down, then I would have a DI which is negative. So in the case where I would be ramping down the current, then I would eliminate that minus sign in that case. If it's a case where I would be turning up the current, then I'd have to consider the directionality of the current. And so in the end, basically what I'm saying is that the minus sign really should just be a plus sign because I didn't take a more rigorous approach to how we evaluated that integral of the current. The key point, the important part about this whole exercise is the fact that the momentum is the same. So no matter what point of view I take, whether I'm saying what is the momentum stored up in the field, or what is the momentum that you get when a force is pushing the charges along the conductor, you in the end get the same result, which hopefully makes sense because momentum is conserved. The momentum we have in the fields has got to be spent or transformed, can be transformed into something, and that something is the motion of the charges in the conductor. So if you put it all together, the picture is kind of self-contained. That you can either say the motion of the charges stores up momentum in the fields, or if I have momentum in the fields, I can impart them into charges and have those charges move.